Okay, so the last set of quadrilaterals. So let's kind of like refresh our memory a little bit about what we did. So the very beginning of this unit, the first day, Monday, right? We talked about polygons, right? We talked about like, you know, hexagons, heptagons, octagons, all those things. We talked about equilateral, equiangular, and regular polygons. We talked about polygons that were concave or convex, right? And we also found like the interior angle sum by taking the number of sides, subtracting 2, multiplying by 180. That gives us the number of the angle sum of any polygon. And then I told you guys we're going to kind of get and focus in on quadrilaterals, right? So we did like Tuesday, we did parallelograms and learned all those properties. Talked about squares, rectangles, and rhombuses yesterday, and then today we're going to finish off quadrilaterals by looking at kites. Ramel. Okay. Yes, you were. And trapezoids, okay? These are the last two quadrilaterals that we are working on, okay? So, if you want to turn the page there, we'll look right at kites first, okay? And a kite gets the name, right, the kite gets the name kite because it looks like a kite, okay? The kite that you fly, right, okay? So, the properties of a kite. Well, if you kind of look at it here, we can kind of see some of the properties. So, what makes a kite, I should go real quick here because there's the definition of kite. A kite is a quadrilateral with two distinct pairs of congruent consecutive sides. So not the opposite sides are congruent, but congruent consecutive sides. Those are next to each other here. So for example, SR and QR are congruent, and then QP and PS are congruent there. Okay, did you have a question, Jason? Okay, so that's one pair, that's the other pair. Notice they're next to each other, they're not opposites, right? The opposite ones are not congruent, in fact. So that makes this thing a kite. So what are some properties then? Well, if a quadrilateral is a kite, then its diagonals are perpendicular, and you can kind of see that here. We drew the diagonals in, they're drawn in for us, we see they do make a right angle there. If a quadrilateral is a kite, then exactly one pair of opposite angles are congruent. So only one pair of opposite angles are congruent. Again, you can kind of see it here. It's these two, right? These two angles do not look congruent at all, right? R and P look like they're completely different. This one's, angle R is much bigger than angle P is, but Q and S, they look like they're about the same, and they are. That's the only pair of opposite congruent angles there. If a quadrilateral is a kite, then one of the diagonals, only one of the diagonals, bisect the pair of non-congruent angles. So, like, for example, this diagonal, okay, it bisects these two angles, this angle right here and this angle right here. Angle R and angle P are bisected. Q and S, they are not bisected, okay? And again, you can kind of see that. This angle right here looks smaller, a different size than this angle, and this angle right here looks a different size than that angle, right? These two are bisected. All right. Yeah, sure. For right now, that's fine. Okay. And then, if a quadrilateral is a kite, then exactly one diagonal bisects the other. And again, you can kind of see that here. Which diagonal is the one that's being bisected here? Is QS being bisected, or is PR being bisected? Yeah, QS is the one that's being bisected, right? Because PR, you can see, the QS is not going through the middle, but PR is going through the middle of QS there. So those are being bisected. Okay? So, we can use those properties to help us solve for, of course, parts of a kite. So if we go over to the next page there. All right. In kite ABCD, so here's a kite. How do we know it's a kite? 1, 2 pairs of congruent consecutive sides. Measure of angle BAE is 32 degrees. So B to A to E is 32 degrees. So let's label that. And BCE is 62 degrees. Okay, I'll zoom in on that some because it's kind of hard to see. Okay. Now, Derek, A asks us to find the measure of angle CBE. So that is this angle right here. Okay, so yes? Yes, exactly right, 90 minus 62. So if we look at this right here, from these diagonals, what kind of shape do we have right in here? It's a triangle, and it's a right angle right there. Exactly right. So we have a right triangle. So yes, Zari is exactly right. We're going to do 180 minus 90 minus 62. She skipped the step and just said just do 90 minus 62, which is a shortcut for it. But that's all we have to do there. 180 minus 90 minus 62 because we have this little right triangle in there. She recognized that, and that's important. We want to recognize those shapes, right? Yes, we're in the quadrilaterals unit, but we can still use triangle properties, okay, to still work. And so we get 28?
Yeah.
28 degrees. Okay, so that's that angle. Just using the properties that we have there.
There's another right angle in this one too, on the 32, right?
And yeah, this is a right triangle as well, because that's a right angle. These are all right angles. So all four of these little triangles right here are right triangles. Okay.
You're not doing the same steps.
So then, yeah, for letter B, asked to find the measure of angle ABE. And so, right, it's the same steps. Is that what you're trying to say, Jason? It's the same steps? Yeah, it's 180 minus 32 minus 90. And so we get 58, I believe there. Is that right? Yeah. Yep, 58. Okay. Derek? Mind your business. Let's not do that.
So that means everything that's on the top one has to go on the bottom triangle.
Exactly right. So that means this angle would also be 28 degrees. This angle would also be 58 degrees as well. Okay. Yeah. In fact, let's find the measure of angle ADC. What would that have to be? So ADC, that's the big angle here. That's made up of these two smaller ones. How can we find the measure of the full angle ADC? Yeah, it's 58 plus 28, right, because this angle is 58 degrees, because that's what we got for the angle up there, and then 28 degrees right there, and so yeah, it'll be 58 plus 28. Okay, which is 66, 86?
86.
I think the answer is 86. Okay? That's it. Just using the properties of the kite. That's how we can kind of example of how we can use those properties.
That's how we figure out the kite.
Okay, go fly a kite. Sorry?
What were the other two?
So like this one right here? Well, what do you think that one is going to be?
32.
It's going to be 32 as well. Yes, this diagonal bisects angle A. So this one will also be 32, which means the full angle there is going to be 64. Right? Oop, Ramel, this is for now. Okay. There you go. And then if this angle right here, Jaden, if this angle right here, BCE, is 62 degrees, what does that mean ECD has to be? 62 as well. I know I'm like running way out of space there, but there's how you can find it, okay? The only other relationship here that's not marked in, that we haven't talked about, BE, is the same as ED, right? This diagonal is bisected by that diagonal AC. We didn't talk about that, they didn't have us use it, but that's the idea. Okay? So there it is. All right. Let's move on then. So that's kites. That's it. All right, and the next one we're going to talk about the last quadrilateral we're going to concern ourselves with. All right? Those are trapezoids. Okay? So a trapezoid is a quadrilateral with at least one pair of parallel sides. Okay? So that's our definition of a trapezoid. At least one pair of parallel sides. I don't know if this is of any interest to you, but this is how messed up our book is. So a trapezoid, here it says, a trapezoid is a quadrilateral with at least one pair of parallel sides. So according to this definition, is a parallelogram a trapezoid? Does a parallelogram have at least one pair of parallel sides? Yeah, it's got two, so that works. So according to this definition, okay, in the book, a trapezoid is a quadrilateral with at least one pair of parallel sides. That means a parallelogram would also be a trapezoid. Okay, not a problem. But if you flip to the back of the book, which you don't have to, I'll do it for you if you want, all right? But if we go to the back where the glossary is, which is where they have things defined, all right, ready for this? It says here, a trapezoid is a quadrilateral with exactly one pair of parallel sides. So, does that mean a parallelogram could be a trapezoid? Does a parallelogram have exactly one pair of parallel sides?
No.
Parallelogram has two. So there's two different definitions for the same word in our book. That's kind of confusing. So which one's right? We're going to go with the one that's right here. Okay, we're going to go with the one that's right there. So a trapezoid is a quadrilateral with at least one pair of parallel sides. So that means parallelograms are trapezoids, okay? Now, in trapezoids, we have some names of things. The parallel sides are called the bases of the trapezoid. So here's a picture of a trapezoid. You can see these two sides are parallel, so they're called the base. And then the other two sides, the non-parallel sides, those are called the legs. All right. If you look over here, we have another shape, also called a trapezoid, but it's an isosceles trapezoid. Now, why do you think we call this trapezoid an isosceles trapezoid? What makes it isosceles? Here, I'll just kind of zoom in a little there. What do you think makes that trapezoid an isosceles trapezoid? All the sides are uneven in this one? Two sides are what? Yeah, they're equal. Remember, what does that word isosceles mean? When we talk about isosceles triangles, how many... Oh, careful. In an isosceles triangle, not all the sides are the same. How many sides are congruent in an isosceles triangle? 2. So we have 2 sides congruent here in the isosceles trapezoid as well. Okay, the legs. And then the bases are right here. Notice, folks, right, the base doesn't have to be the bottom side. Here the base is this and this side. Why? Oh, gosh, never mind. I see what you're saying. They're marked congruent. Man, this book is way messed up. That is not, those are not, clearly not congruent. But they're supposed to be parallel. Okay? So these two are the bases because they're the parallel sides there. Okay? Excuse me. A trapezoid has 2 pairs of base angles as well. So now we're talking about base angles. Each pair consists of the 2 angles adjacent to one of the bases. So these are the base angles. Okay? But these are also base angles as well. They're the pair of angles that kind of touch the base there. Okay? So those are base angles, and then those are base angles. These are base angles right here, and these are base angles right here. Because these 2 angles touch this base, so they're a pair of base angles, and these 2 angles here touch this base, so they're both base angles. Okay? Yep.
Would a trapezoid technically be like a square too, in like a rectangle?
So a square is technically a trapezoid, yes. But a trapezoid is not necessarily a square, right? I mean, if you look at this is a trapezoid, but it's definitely not a square, right? Yeah. But a square is, yes, a trapezoid for sure. And a rectangle is a trapezoid, and a rhombus is a trapezoid, because they all have at least one pair of parallel sides. So, yeah. Okay? All right. Properties of isosceles trapezoids now. Okay? If a quadrilateral is an isosceles trapezoid, each pair of base angles are congruent. Okay, and again, you kind of see that. If we look back here, it's like, yeah, those 2 angles look congruent, and yeah, those 2 angles look congruent. Base angles look congruent. Okay, so makes sense in the picture there. If a trapezoid has 1 pair of congruent base angles, then the trapezoid is isosceles. So that's like the other direction. Okay, if the base angles are congruent, then the trapezoid is isosceles. And then finally, a trapezoid is isosceles if and only if its diagonals are congruent. So that's like the rectangle, right? The diagonals here would also be congruent. Okay, so congruent diagonals right there. Okay, congruent diagonals. All right. Let's look here. So we got some measures and values we want to find. All right, so let's go to page 475. We're going to skip those proofs because we don't need to do them. Okay. Got some examples here on page 475. All right. So, example 3 here says, find each measure or value. So a railroad bridge has side sections that show isosceles trapezoids. So here you can see there's an isosceles trapezoid. Okay. The figure ABCD represents one of those sections. AC is 13.2. So from A to C there is 13.2. I'll kind of try and draw that in if I can fit it there. Okay, 13.2. BE is 8.4. So like this section is 8.4. And we want to find the length of DE. Okay, that's what we're trying to find there, the length of DE.
Wouldn't it be the same thing?
So BE is not the same as ED. So in a isosceles trapezoid, the diagonals don't necessarily bisect each other. So BE and ED won't necessarily be the same length. But BD is the same length as what? AC, that's right. The diagonal AC is the same as BD.
Yeah, so if you subtract it.
Exactly. So if we say the BD is 13.2 and this piece of BD is 8.4, if I want to find the other piece, we'll just do
Subtract
13.2. Yep, minus 8.4. Exactly right. Very good. Okay. And when we do that, we get 4.8. Okay, so 4.8 is that length there. Now again, if you look at the picture, that doesn't really make sense because BE looks smaller than ED does, but the math holds up, so we're going to stick with it. We're going to, believe that over the picture there. But anyway, there it is. Okay? So again, that's just using the properties, using the fact that the diagonals and a trapezoid are congruent. All right, questions on any of that? All right. Let's flip over here to this next one. Okay, letter B. Find the value of x so that trapezoid EFGH is isosceles. Okay, so if you look here, we've got a pair of one pair of parallel sides. So this is definitely a trapezoid, but we want to make sure it's an isosceles trapezoid. Well, what must be true about angle E and angle F? How should they be related to make this an isosceles
They
trapezoid?
should be...
How can we relate those two things? What do we want to be true about them?
Are they equal?
They need to be equal. So 3x squared minus 4 equals 2x squared plus 21. Yep, let me just get everyone, make sure we're okay, and then yeah, you can take it away there. Okay? The two base angles here, these are base angles, right? They touch this one base. They need to be congruent if the trapezoid is going to be isosceles. We want it to be isosceles here, so we set them equal. All right, so yeah, so Zaria, what are we going to do here first?
Subtract 2x squared.
Yeah, so this is kind of weird. We have x squareds in here. We haven't done a whole lot of equations with this, but it's actually not, it'll end up not being too bad. We'll subtract 2x squared from each side to get those like terms together. And yeah, so 3x squared minus 2x squared is just 1x squared. I'm just going to put x squared, though. It's the same thing. Okay, minus 4 equals 21.
And I added 4.
Add 4 to each side. X squared equals 25.
Equals.
Yep, so square root, and we get, I'm running out of room here. We'll say x equals 5, or, and I don't know if you guys remember this from algebra last year, but when you take a square root in an equation, when we do x squared equals 25 like that, 5 is an answer, but so is negative 5. Both of those are okay answers here. Okay, when you square root 25, or when you have x squared equals 25, both 5 and negative 5, when you square them, give you 25. So that's why we say both answers there.
Do you have to put those answers?
You should in these kind of situations, yes. Because again, in an equation setting, you want to find the value of x so that this trapezoid is isosceles. So both of these values of x work. I know it does just say find the value, but it's actually values. There's actually two that work there.
So you'd have to put 5 and negative 5?
Those are both possible answers.
Because like when we had to do squares, we didn't have to put a negative number too.
When you do square roots.
I mean, yeah. Square.
So when you see something like this, Haley, and everybody else too, when you see something like this, that is equal to just plain old 5. Not positive or negative 5, just positive 5, that's it. But when you have something like this, you want to find all the values of x that make this equation true. And in this case, there's two values. If I put a positive 5 in here and square it, I get 25. If I put a negative 5 in here and square it, I get 25 as well. So both of these are correct.
Do you want that 5 is correct?
Actually, the directions just say find the value of x. So we actually don't need to find the actual angles here.
I did it, but if you do it, it comes up to
Yes, and you should get the same answer either way.
class
What was the answer?
71.
71? Okay. So you get 71 degrees. Is that okay, or are you still thinking about that?
I mean, like when we had to find the square root before, we didn't have to put in a negative number too.
Right.
Like the other problems that we were doing.
When you're doing like equations with squares,
Yeah.
and when you square rooted both sides, you didn't.
Yeah.
Oh, back like when we were doing other problems, you mean in the
Yeah.
past? Oh, with like Pythagorean theorem and stuff like that. Great. So good question. Why didn't we do it there? Because in those problems, for example, we were talking for Pythagorean theorem. We're talking about sides of a triangle. It doesn't make sense to have a -5 length for the side of a triangle. In this case, though, the -5, when you will square it, multiply by 3 and subtract 4, it gives you a positive 71-degree angle, even when you plug -5 in. Zari just did it. She got a 71-degree angle there.
So with any problem like that we're gonna have like that, either one would work.
I'm not going to give you one with square. I mean, you might see one later in your homework, but you won't have to worry about it for the test or anything like that. I don't want to give you something with squares in it or anything. So, but like in the future, in Algebra 2, for example, when you guys get to Algebra 2, if you see squares like that and you square root, you want to include the positive and negative answer. Sometimes you throw out the negative answer if it doesn't make sense in the context of the problem.
Would this like be on like the benchmark?
Nope. No. Kelly's like, whoop, forgotten then. Okay, so yeah, okay. All right, let's take a look at these, and then we'll be done. I'll give you guys your assignment. So 8 and 9, and then we'll stop. Okay. So number 8, we have an isosceles trapezoid PQRS, and we're asked to use same side interior angle postulate to find the measure of angle R. So we want to know this angle right here. Okay. Well, since this is an isosceles trapezoid, angle P must be congruent to what other angle here? Yeah, not angle S, Q. They're base angles. So this is also going to be 77 degrees. Okay, but that's not the angle we're interested in. We want to know angle R. You'll notice here it gives us a hint. It says use the same side interior angles. You might be like, wait a minute, same side interior, that's what we talked about way back when we talked about parallel lines crossed by a transversal. How should these two angles be related? If we have a parallel line here crossed by a transversal, how should these two angles be related? Supplementary. So to find this, what can we do?
Minus 180.
Not 90 minus, 180 minus. 180 minus 77. Looks 103 degrees. So that's that angle right there. So if angle R is 103 degrees, what does that mean angle S has to be?
Angle S is 103 degrees.
103 degrees as well. You got it. Exactly right. Okay? All right, last one here, and then I'll give you guys your assignment. We'll be done. Okay? JL is 3y plus 6, so that's J to L there. KM, 22 minus y. Determine the value of y so that JKLM is an isosceles trapezoid. Well, if JL is 3y plus 6, and KM is 22 minus y, how should the diagonals be related in an isosceles trapezoid? The diagonals should be what? JL, how should that length be related to KM here for this to be an isosceles trapezoid? They should be what? Yeah, equal. So we can just write 3y plus 6 has to equal 22 minus y. Okay? And so we have 3y plus 6 equals 22 minus y, so we can add y to both sides here. Okay, we get 4y plus 6.
Why would you add
To cancel the minus y. Add it over. Did you subtract 3y from both sides? Or what did you do? Okay. So we get 4y plus 6 equals 22, subtract 6 from both sides. 4y equals 16, and then divide both sides by 4. We get y equals 4. Okay? And so there it is. Y equals 4 there. Okay? So that's the value of y. 4 is the value of y that would make these two diagonals equal and therefore make that an isosceles trapezoid. All right? So that's what we're going to be doing today. Your assignment's just going to have trapezoids, isosceles trapezoids, and then kites in it, okay? And you're just going to use the properties to solve for the missing pieces and things, okay? So let me give you guys your assignment then. And you guys have a good half an hour to get it done. So hopefully you shouldn't have any homework this weekend, okay? Now we can all go to the game and not have to worry about geometry. Although even if you did have geometry, I'm sure you wouldn't worry about it.
I know, right?
I was like,